Thank you very much, and thank you all for coming. So today I'm going to be talking about some work that I've done with James Cheney and Vashti Galpin. Sorry, just going to get my stopwatch on. James Cheney and Vashti Galpin on how we can use language-integrated query technologies to allow, much more prevalent and idiomatic temporal queries. So I'm going to start off just by talking about, well, what is temporal data, right? And temporal data is very prevalent. You can see temporal data, in many different applications. Here's a sort of meta kind of thing here, where we've got the revision history on Wikipedia for the transaction time page. And what we can do here is we've got every single version of this article that ever existed, and we can go and roll back to whichever one, at every time that it was updated, for example. Another kind of big domain for temporal data is HR records, for example. So, I mean, when you are in an organization, you're going to get promoted, you're going to go and change positions, you're going to go and change jobs, you're going to change salaries. You're not going to be the same thing for long, right? And what temporal data allows you to do is actually have a look and see at what somebody was at a certain point in time or will be at a certain point in time. Now, doing operations on temporal databases is very tricky, right? It's easy to try and hand roll something yourself and get it very, very badly wrong. You can try and do intervals, and then you have to think about, well, what about primary keys? And it turns out that there's been a wealth of research on temporal data going back to the 1980s, and this culminated in several language designs such as TSQL2, but more recently, actually, an actual addition to the SQL standard as part of SQL 2011. The problem with this, though, even though it's been standardized, it's not widely implemented. So there are only a handful of database management systems, such as Oracle and Teradata, which are proprietary, and they have limited support for temporal queries. So a lot of the time, if you're using a stock DBMS, you're going to have to go and implement it all yourself. You're going to have to learn all the database theory, you're going to have to go and learn all the implementation strategies, and then you're going to have to put the effort in and actually write it yourself. And this is, annoying to do. It's brittle, it's error prone, and you're going to end up writing, code that's not idiomatic. So there has been this very nice textbook by Richard Snodgrass on actually how you can emulate temporal functionality in SQL. And it's a really, really good book. But still, all that gives you is the recipes to do this yourself. So we had the idea of, well, there's a technology known as language integrated query in the kind of functional programming databases world. And what this allows you to do is, instead of writing, say, kind of standard SQL like you would up there, standard strings, you can write the code as if it is in your language, right? So if you're familiar with list comprehensions, for example, this is a list comprehension, and it kind of looks as if you're iterating over that particular table. So for every X in to do, you're going to check whether X is done, and if so, then you're going to return it. And that would translate directly into that. So you wouldn't actually do the iteration, but there are various pieces of work which allow you to normalize it and generate very efficient SQL. So in the past, what we've done is we've actually done a kind of large-scale pharmacological database, and we've shown some quite nice efficiency results using language integrated querying, for example. And also, we can get static type checking of queries and splice things in, and it's all very modular as well. So our idea is to support temporal queries via query rewriting. So can we use language integrated queries to get temporal data functionality for free? So the kind of core contributions of this paper are threefold. So we've got core calculi. So the idea is we've got two core calculi, one for transaction time and one for valid time. And I'll get on for those, to those in a minute. And we translate those down into a non-temporal language integrated query calculus. Then we look at the idea of a sequence join. So that's if you've got different tables which are both temporal, how would you join those together? And we derive a kind of language abstraction for that. And a very simple translation strategy which allows us to do that really neatly. And finally, we implement this in the LINQ's functional programming language, and we implement a non-trivial case study based on curating COVID-19 data. Okay, so let's have a look at transaction time. So transaction time models when a fact was stored in a database, right? So we've got this to-do list over here. Go shopping, cook dinner, walk the dog, and watch TV. And the idea is, what we do is we also augment the data with two columns here, which give us a timestamp, basically. So this says that all of these four things were entered into the database at 11 o'clock, and they are currently valid. So that's what the infinity sign means. Now, the idea here is that the database grows monotonically, so the data is never lost. And our modification operations instead manipulate these two timestamp fields that we've got there. Now, importantly, in transaction time, since we're all only talking about how the database has evolved over time, the timestamps only refer to the past, apart from the forever one. And finally, the users do not modify these fields directly. It's all done by the underlying system. So let's have a look at a couple of examples here. So we've got this to-do list, and say we want to go and check off cook dinner at 5:30. So what we would do is we would write a kind of bog standard update query here. And instead of doing a destructive update, what we would do is we would close off the previous row at 17:30, and then we'd start a new one with a new value at 17:30, valid forever. So we've not lost that data. Now, how about if we decide at 17:30 or 1900 that we don't want to watch TV anymore? We've not got any time. So what we can do here is, well, we can just close off that row there. And then after 1900, that row won't be kind of relevant to the database anymore. And then what we can do is we can do time slicing. So we can check what the state of the database is at a given point in time. And we can do that manually by, sort of specifying the ranges. Or since, we've got this nice pluggable language integrated query, we can just do a very simple for comprehension there using this at function, which just gets us the state of the table at 1800. We can also do kind of interesting kind of sequence queries here, such as, well, when was it recorded that cooked dinner was completed? Or give the change history for cooked dinner, for example. So have a look at how this has varied over time. Okay, so that's transaction time. So how about valid time? So valid time differs in that it models when a fact was true in the modeled reality, right? So this is the domain that you're modeling, whereas transaction time was the database and how that changed. So here we can have that timestamps can refer to the future as well as the past, and that users can actually modify these timestamps directly. So you might want to extend somebody's employment contract, for example. Now, there's also a quite cool thing that you can do, which allows you to apply an update or deletion over a time period. So these are called sequenced updates, and I'll give you some examples of this in a minute. So we've got this kind of academic HR database, and the first thing that we want to do is we want to hire in Carol as a professor on a permanent contract. And you'll see down here, we just write a normal insertion, and we get the from and to fields populated automatically. If we do a current deletion, then we delete from the employees where the name is Alice. So what that does is then that closes off the to row at the current moment in time. And then what we can do is we can say, well, Carol's going to be head of school between 2023 and 2026. So this actually ends up giving us 3 rows, right? So we've got the point where Carol's a professor before she ends up as head of school, so that's 22 to 23. Then it's the period where she is head of school, so that's between 2023 and 2026. And then it's the period afterwards when she's kind of reverted to being a professor, and that's from 2026 onwards. And again, we don't need to do anything particularly fancy here. We've just got a very kind of straightforward update where we just have this kind of between clause here saying that we want to go between, apply this update between 2023 and 2026. There you go. Thanks. Another thing that we might want to do is actually modify these things directly. So extending Bob's contract until 2024. With a valid time system, we can actually do that. So we can actually say in our set clause that we want to go and set that as being valid to 2024. So we formalized all of this. I'm not going to go too detailed into the formalism because I don't have a huge amount of time. But the key idea is to define a direct semantics for these temporal operations. We've got quite a few of them in the paper. And then show translations into a non-temporal language integrated query calculus. So we've got a type system, and as is normal for sort of higher order calculi with database access, we use a type and effect system. This basically says that under typing environment gamma, term n has got type A and produces effects E, right? And that can be either a read effect or a write effect. And by looking at this information, that then allows us to be very specific about when we can generate queries and get efficient SQL out. The second judgment that I'm going to be talking about is the evaluation judgment. So we use a big step judgment here. And this is saying that I want to evaluate term n with respect to some database delta timestamp iota, resulting in a final value v and an updated database delta prime. Now, this is the most complicated rule I'll show you. So this is the transaction time update rule, right? And what that is saying is, well, we're updating from some table L. So the first thing we do is we evaluate that down to a table. And then what we wanted to do is, for every time that n matches a particular row, then we want to go and set all of those L's, n's, all of those labels to the value which is going to be n. So what this is saying here is, well, we're going to create a bag of bags for every value in that database. And then we are going to split it in two, right? So what we've got here is, well, if we from start until end, if that predicate matches, so that goes to true, and we get our new values vi, and the end there is infinity, meaning that it's current, then we'll get those two new rows there, and then we'll end up flattening them down. Otherwise, that data is just going to be untouched. So this shows how you can get two different rows out of just the one particular temporal update. And what we can do now, as well as having the direct kind of semantic rule for it, we can show how you can do a translation into a non-temporal calculus. Now, again, don't look at this in too much detail, but there are three basic things that we're doing here. We're calculating a set of affected rows, and they have got the new values. Then what we're doing is we're updating the previous rows, and we're kind of setting their end period to now, so they cease to be current. And finally, we are inserting the things that we calculated up there. And this allows you to kind of prove a semantics preservation property, saying that the non-temporal semantics can simulate the temporal semantics. Also, we get a strong type soundness property, and similar results also hold for VLINQ. Now, the final thing I'm going to be talking about is sequence joins. So what we've got here is, well, say we've got a kind of temporal table joining with a non-temporal table. And this is quite easy to do. So what you end up doing is, well, you do a query over the employees table, query over the salaries table, and what you just do there is you kind of join on the bound field, and then you create a new row with the start and end rows that you had before, right? So this is all well and good. And this will get you something a bit like this, right? So we end up having the names of employees, the salaries, and the original to and from fields. Now, it gets slightly more tricky when instead of doing a temporal table with a non-temporal table, we're now doing two temporal tables. So what we've got here is, well, we've got our employees database. So Alice is on A08 between 2000 and 2008. A09 between 2008 and 2020. But what we've also got is a temporal salaries table. So what we've got over here is we've got A08 is £40,000 there, and it's £40,000 there and £41,000 from 2015 onwards. So what we then need to do is we need to kind of pair names of employees with their salaries at each point in time. So we can do this, and what we end up getting is 3 rows for Alice, right? So we've got the point at which she was on A08 between 2000 and 2008 before she got promoted. Then it's the point after she was promoted between 2008 and 2015. And then it was the point at which the salary then got bumped up. So you kind of get that sort of matching between all of the different kinds of periods of validity. You probably wouldn't want to write the code to do that, but it turns out that you can actually, what we've done, in fact, is a very straightforward construct just called join, and that allows you to just concentrate on the data, and then the underlying system will do all of the wrangling with periods of validity for you. And the key idea here, I'm not going to go into the details, but it's a very straightforward translation on normal forms. So the theory behind language integrated query gives you this very rich kind of literature on how to get things in a very kind of compact normal form. And then if you do a translation on that, you can very easily support this. So we've implemented this in the LINQ programming language, and we have got a case study based on curating Scottish Government COVID-19 data. And the idea here is that valid time is a representation of kind of revisions to the data that come in each week. So just ever so slightly over time, but not much. So today I've talked about kind of temporal language integrated query. So we've got transaction timetables, which track the states of databases, valid timetables, which track the state of the modeled reality. We've got these native calculi, which are then translated into kind of standard calculi, which then admit efficient SQL translations. And we've got also sequence joins, which we get pretty easily, in fact. This is all implemented. And there are 3 things that we want to look at next. So the first one, I'm really interested in looking at how we can do nested sequence joins. So at the moment, sequence joins only work on flat tables or flat end records. And doing that in a nested thing is substantial, kind of needing to think about things. By temporal databases as well, we're trying to look at how we can do this in a kind of more compositional way. And finally, we're quite interested in seeing how we can do some stuff on scheme revolution as well in the language integrated query setting. So that's it. Thanks very much.
Do we have time to question? Here comes. Yeah. Yeah.
Is it here all listening?
Right? Do you hear? Subtract. So, can you hear me? Okay. So, thank you very much for the excellent talk. And I want to ask many questions, but
oh, great! Please go ahead.
but you listed some future books, but so about what you have already done. So you skipped the transformation to normal forms. Can you say something? So well, at the beginning, well, so it seems very difficult to transform a query with temporal data.
Okay.
So, please.
I wish I'd got a bonus slide for this, but I thought I just wouldn't have time. So essentially, what you need to do is you can define functions which calculate the overlap of multiple different time fields. And then once you've got things in a very predictable form, all you then do is you calculate the kind of Cartesian product of this, and you just kind of narrow it down using the overlap functions. So essentially SQL does it for you.
Okay. So right now you don't have nested sequence
Yes.
joins.
Yes.
I'm very interested in that. Do you have any future plan for that?
I really want to do it. It's the thing that I'm most interested in about this work, I think, this kind of work program. And the reason is, so in the Guide to Pharmacology book that we did, The reason that we get such expressiveness and such kind of such good performance results in terms of query count in particular is because we make extensive use of nested queries. Now, it would be nice to just treat everything as a transaction time table, but because we can't do the nested joins, the nested sequence joins, that's a kind of big barrier. Now, the problem is when you've got a nested inner record, that might result in nested outer records. So you need to, I think there'll be quite a bit of kind of conceptualizing how this will go. It's non-trivial, and you know, even though the translation for kind of flat sequence joins is very easy, I think there's quite a lot more conceptually to think about with the nested case.
Okay. So even so we did we added group by groups to James Cheney's calculate on. Well, it was a big challenge for us. So maybe so yes. What last question?
Yes.
Okay.
Yeah, I mean, I guess just following up from that question.
Yeah.
Can you hear me?
Yeah.
Do extensions to this sort of query normalization technology broadly just work in the face of the temporal stuff, or is grouping, aggregation, nested data, not just nested sequence joins? Do all of these extensions, are they all orthogonal to adding the temporal stuff, or?
Nested data is fine. A lot of the additional ones you do need to be a lot more careful about. And with, there's a big kind of work program that this is open, that we started looking at this thinking, all right, this would be an interesting thing to do. And then, we've got quite far with it, but I think, thinking of all the different cases makes it sort of think, well, do we need something a bit more kind of general basic, and then go from there.
I had a very quick question. I didn't hear what is a bitemporal database?
A bitemporal database, sorry, I should have said that. A bitemporal database is one where you have transaction time and valid time at the same time.
Could you say again?
So a bitemporal database is one where you have transaction time and valid time at the same time. So you can think about, queries such as, when was the point that Bob's contract was extended, for example. It's very rich theory, and we want to see whether we can get that in a compositional way. We can't at the moment, but I think that's the next big thing to look up.
It's your next challenge.
Yes.
Okay. So let's thank the speaker again.
Thanks very much.